This video is part of a course on food physics. Uh, Here we're talking about microwave heating. That's really in two parts. In part one, we have the electromagnetics, and then part one is in 6 sections. So this is section 5 of those 6 sections, talking about food factors in microwave absorption in heating inside a microwave oven. This is part 1.5, and here are all 6 sections. We are here talking about food factors in microwave absorption. The video just before this was this microwaves inside a microwave oven, and the following video is oven factors in microwave absorption. Some of the important factors affecting microwave energy absorption in food in a microwave oven are shape, size, aspect ratio, dielectric properties, and if there is any other active packaging material like a metal film in it with the food. So we're going to talk about this, but two comments. One is that do not expect to see some very clear formula or figures that shows perfectly what any one of these uh, factors does. That's just difficult because the situation is quite complex, and it's complex because these factors that you see here, shape, size, aspect ratio, dielectric properties, or active packaging, they interact with each other. They cannot be considered in isolation. And so that makes the whole situation quite complex. So first, we would look at the shape effect. We will talk about two different aspects of the shape effect. The first one is talking about what happens in corners and edges. And you might have observed that microwave heated food is hotter, and the edges and corners are particularly dried up at corners and edges. And so if we think of just using plane waves coming in incident on a food surface, notice because food has a higher dielectric constant than the surrounding air, then the waves are going to be refracted, and they will get closer to the normal, so they could do something like this. If we think of another wave here, that will also do the same, and the net effect of all of these is that they will converge somewhere inside, closer to the corner or the edge. In other words, due to the convergence, energy is concentrated around the corners and edges. This kind of effect is enhanced in a spherical object. So in this case, even though it says the material is egg white, and it looks kind of like like an egg, but it's a sphere, and the spherical object with the food properties is being heated in a microwave oven, and it is a full-blown electromagnetic simulation solving the Maxwell's equations inside an electromagnetic inside an oven, and that's what gives us the profile. The red stands for higher electric field, blue stands for lower. So you can see that there's quite a bit of sort of enhanced electric field uh, deep inside, and it's basically the same kind of effect that we were talking about before, that the refracted angles are smaller than the angle of reflection. Angle of reflection would be like that, and it is that effect enhanced. So if we think of if it's a sphere and it's coming in like that, another wave coming in like that, so it's going to cause enhanced heating inside. This is also referred to as the focusing effect of the shape, the carved shape. And one of the examples of this is, for example, the egg blowing up is partly because of this. It's partly because of the enhanced heating inside the egg because of its carved shape. And those are the only two effects of shape we're going to talk about for now. Shape effect will come back again later in the discussion. Another important factor is the size of the food. This figure here plots the absorbed power in the food with the various volumes. As we increase the volume is in centimeter cube, and it is being done in a cylindrical container. You can see that full-blown cavity simulation or experimental measurement, they follow nicely the same curve. As we increase the volume, as we go this way, increase the volume from a small to large, the amount of energy, the power from the oven that is absorbed by the food increases, as you can see. So the total power increases until some kind of a threshold volume, after which it kind of stays constant. Of course, the power absorbed cannot be more than the oven power. Now suppose I want to think of a food absorbed per unit surface area. So of course, as the volume increases, the power absorption increases, but as the volume increases, then the surface area also increases. So what does it look like for power per unit surface area? So Watts per unit surface area looks like this. So if we think of some sort of a flux, like it would be in conventional heating, watts per centimeter square, that goes down like that as the volume increases or the total surface area increases. By the way, a glass of water, for example, is about 250 cc. So which means this curve shows by the time you're talking about a volume of a glass of water, then the food in this kind of a high lossy material like water is absorbing the most amount of power that it can. Another factor in microwave absorption is the aspect ratio. This figure shows absorbed power, total absorbed power in the food in watts as the food is kind of flattened. So the surface area over volume keeps increasing. So for this high loss material, that is ham, where the microwave power is absorbed mostly near the surface because it's very high loss, the absorbed power increases with aspect ratio. Now, this may not be true for a low loss material. So as we started this section, I kind of promised that we cannot always come up with sweeping generalization and very clear-cut statements of different effects. And so here's an example. For surface area controlled heating, higher aspect ratio increases the power absorption. And it's very hard to generalize. At least we do not have easily available information for all kinds of material. This one is for high loss material like ham. Another important factor in microwave energy absorption in the food in a microwave oven is, of course, the food dielectric properties. As already discussed under dielectric properties, the food dielectric properties cover a huge range. Microwave power penetration also varies significantly. So you can see, for example, meat juices or which would be kind of like the soups and so on have a much smaller penetration depth, like here half a centimeter, 5 millimeter, whereas frozen foods can have much larger penetration depth. So penetration depths also cover a huge range. Let's look at the effect of these properties for some specific combinations of situations. We have chosen spherical foods to study the effect of dielectric properties on the microwave absorption. And we are going to do this for two groups of food, two different sizes. First, for the large radius. What is plotted here, I have to explain the y-axis. Its heating potential is the rate of heat generation, the volumetric heating at any radius averaged over all angles theta and phi. So it's like average of the heat generation for a shell at radius r. That's what the heating potential is, but again that is also normalized by the maximum value, and that is plotted with radial distance here. So this is for the large radius, and then we have the same for small radius. So for the small radius, and you can see the effect of dielectric properties are brought in through different materials that have very different properties. So frozen foods having the least microwave absorbing, and then something like ham that has quite a bit of salt is very highly microwave absorbing. So it covers a big range of dielectric properties. What you see is that almost all foods of this smaller size, so in this case you see the radial distance, it goes up to 1.8 centimeter. So these are 0.8 centimeter radius spheres. For the smaller size, they behave, for all different food properties, they behave similarly in terms of energy deposition with radius. Okay. Most energy is deposited near the surface. At the larger radius, penetration depth plays a very significant role. Foods with longer penetration depths, like this frozen vegetable here or water. So this, by the way, is pure water without any ions or any salt in it. So for these longer penetration depths, there is significant focusing. For the smallest penetration depth, that would be ham, because it's salty, plus it has quite a bit of water, so it has a very small penetration depth, and for that there is no focusing. By the way, focusing has to do with this effect, that the heating potential or the averaged uh, averaged overall angle, the microwave energy deposition, it actually increases for water and for frozen vegetable toward the center, toward the center. Um, so instead of uh, things being heated more near the surface, it's actually heating more deeper and deeper inside. And that is what we are calling as focusing effect. So the focusing effect is there for this other items like frozen vegetable, water, or even potato. But for a very lossy material like ham, then you do not have this kind of a increasing um, heat generation near toward the center. That's not there, and so we say it does not have the focusing effect. So that was how the rate of heat generation varies with radius for two different sizes, small radius and large radius, but the figures are with radial distance. Next, we want to see if or how the rate of heat generation varies with radius. That means the size of the sphere. So here we have plotted concentration index, which is a measure of intensity and extent of focusing effect. So focusing effect is the fact that instead of energy dropping as it would, let's say, for a plane waves in a infinite semi-infinite region, the energy would be dropping. Instead of dropping, then the focusing effect measures if it picks up, as we saw in the previous slide, that in a um, sphere the energy can actually increase toward the center. So this concentration index is a measure of, instead of dropping, how is it picking up toward the center. And it's a rather complex measure that maybe it's not worth getting into, and the details of the exact definition of how it's measured is in this publication. But the index measures, as I said, intensity and extent of the focusing effect in a sphere, and that is plotted with radius of the spheres. So it's not radial distance, but it's plotted with the radius, capital R, of the radius, and as you can see, it goes up to 5 centimeters. Why do we care for this intensity or extent of focusing? Among many reasons, we care because that can give us an idea of how uniform or non-uniform the heating is going to be. Now, another factor that relates to dielectric properties is important in describing this intensity and extent of focusing, and that is penetration depth. So here we have, the wavelength. The wavelength inside the food, which is very different from the wavelength outside. Outside in the air, the wavelength is of the order of 10 centimeter, but inside the food, like this for water, is about 14 millimeters. And likewise in ham, for example, it's about 15 millimeters. So these wavelengths, it has been shown that this wavelength in the food has a lot of influence on the focusing effect. So the smallest wavelength shows the most amount of focusing, and that is for water, whereas the largest wavelength have the least amount of focusing. But it's not just the wavelength. Focusing is less intense for small penetration depth. So ham, as we know, it's lossy, so it has a small penetration depth. So that also very much reduces the possibility of the focusing effect. Foods with longer wavelength and a longer penetration depth have a large range of sizes over which it shows the focusing type effect, although the amount is not as high, but it shows this kind of enhanced heating near the center over a large range of sizes. Again, the focusing is not as intensive, but it occurs over a larger range of radius. That we are in the section where we are supposed to be talking about the effect of properties, and we have been, except that in the last several slides, when we talk about properties, the size and the shape also come into the picture. And so that's why I said early on that these factors are not something we can treat in isolation. It's their combination that we have to discuss, and that's why things get complex. So there is significant interplay of properties, size, and shape. And here is a nice example of it. So this one is for a sphere of 2.5 centimeter radius, and it's a sphere of meat or meat analog. That's the tylose. So it has properties close to that of beef, and this is being heated in a domestic microwave oven, and we have two sets of results. One is from experiment. That's this set, and the experiment is for this the tylose, the cellulose material with 0% salt, 2% salt, and 4% salt. For experiment, so this is using thermal infrared camera. These are temperature values. So how was it done? So you make the shape of the sphere, heat it, and then after heating, very quickly slice into half, because they were actually made from hemispheres. So hemispheres joined together, heated, and then after heating, within few seconds, you split it back in half and use a thermal infrared camera to take these set of images. So their temperatures, they're not heating rates, or they're not power deposition, because we're doing experimental measurements of temperature. And on the right side is full thermal electromagnetic coupled simulation of the Maxwell's equations describing electromagnetic waves, and and calculating the temperatures at the same time for the three different salt concentrations. What do we observe? For the higher salt concentration, this one, it is more lossy. So the heating is more near the surface, like here, more near the surface, because it's very lossy. At the other extreme of 0% salt, it is much less lossy, and so energy can penetrate further in and produce this kind of a focusing or enhanced heating effect closer to the center. So again, to repeat, there is significant interplay of properties, size, and shape in producing the range of energy deposition that happens inside the food, or they all contribute towards the heating non-uniformity that we see in the microwave oven. So if you're interested in details of these pictures, you can go to this paper. To summarize, then, when it's lower loss, then there's more focusing, and when there's higher loss, there's less focusing effect. So and this 2% would be in between. This is the primary conclusion, and a nice way to see the interplay of properties, size, and shape. Next, we want to talk about how two foods with very different properties would heat simultaneously, as would be the obvious application of this kind of trays, dinners that have many different foods together, and they're being heated at the same time. But this is too complex to study and make a conclusion out. So what we will do is we'll have two foods, two rectangular blocks placed in the oven as shown, and those two foods are separated enough so that one is not shadowing the other, and then they are heated simultaneously, and the two foods have quite different properties. And then we are going to do electromagnetic simulation of this cavity, the oven plus the food system, to see how they're going to be heating. So we start with the conclusions that relative power absorption in simultaneous heating of two different foods follows the same relationship as when heated individually. What do we mean here? To answer this, we again get help from electromagnetic simulation. So here we would solve the full electromagnetics for heating in a microwave oven with two food loads. So we're going to solve for electric fields in the oven and inside the food. And these two food loads are, this is food 2 and food 1, and they can be, one can be very lossy. So let's say water, and the other is not much microwave absorbing or very low lossy food like oil. Before we talk simultaneous heating, if we were heating by themselves. So if we are heating just water, then water is more lossy, so it would absorb more microwave power. Likewise, oil by itself, it will absorb less microwave power. By the way, if one is confused that oil sometimes oil heats more than the water temperature wise, that's a separate effect. It's not absorbing more energy, but whatever energy it's absorbing, it's because its specific heat is lower, so its temperature rise is faster. That's a separate effect. Let's not bring that in here. So oil will absorb less and water will absorb more when they were heating by themselves. So the ratio of power absorbed in water to power absorbed in oil for any given volume is going to be more than 1, right? Now let's look at the results for simultaneous heating. So what you are seeing here is when we have these two foods, in this case water and oil, heated simultaneously, then the y-axis is the power absorbed in water in watts divided by power absorbed in oil at any given volume. So if 100 means volume of each material, so volume of each of these rectangular shaped containers is 100, and so for that this is my ratio, so it's considerably higher than 1. So what is the trend here? So the most important conclusion is over the entire volume range from very low to this 400, the ratio is always more than 1, which means water absorbs more than the oil, exactly what would have happened if they were heated individually. Here they're being heated simultaneously. At smaller volumes, here in the small range here, water absorbs lot more than oil because these numbers are up quite a bit, right? It's in this range. And you notice that experimentally also we find the same trend. So for smaller volume, water absorbs lot more than oil. At larger volumes, while water still absorbs more than oil, because you see the ratio here is closer to 2, so it's more than oil. The difference between them is not much, and you can see the trend. They're kind of trending toward being close to the same amount of power being absorbed. We're going to see that this trend at low volume and high volume, it continues for different pairs of food. What we just saw, namely simultaneous heating following the same trends as in individual heating, will now be checked for two different sets of properties. First, it's frozen vegetable and ham here. And what is plotted here is the power absorbed in frozen vegetables in ham with a change of volume, and in each case it's the volume of each material. So it's the power absorbed, but the values are scaled. So the values are divided by the maximum power absorbed, which happens to be for frozen vegetables at this higher volume. So all powers are divided by that. That's why it goes between 0 and 1. So here we see complications. The trend in the previous slide, for this one, the trend was much more clear. Here, it seems like it's not very obvious. But is it? Let's try to dissect it and try to see if there's any similarity between what we already saw in the previous curve. If we divide this into arbitrarily into a small volume and large volume range, okay, then we see in the small volume range that or the smaller volume range, the high loss material ham does absorb more than, so this is for ham and it is more than for the frozen vegetables. So in the smaller volume range, it is totally consistent with the previous figure that the ratio is more than 1. Ratio between what is absorbed in the high loss material to the low loss material is more than 1, and it increases, the ratio increases as the volume gets smaller in this direction. This has been reported experimentally as well. In the high volume range, remember in the previous slide, they got closer to each other. The ratio got closer to 1. So here also you can see that they move in the same direction. They move in the same direction, so power absorption get closer. But we really have to leave it at that because it's not as clear cut and we don't have also as much experimental data to back it up. So then if we look at another set, in this case frozen vegetables and water, again we plotted the power absorbed, but it's scaled by the maximum power, which again is here. So we see the same trend. So as a general understanding then, simultaneous heating follows the same trend in terms of energy absorption as when heated individually. So if we try to put this together, food volume in simultaneous heating, if we are looking at smaller volumes, then larger power absorption for more lossy material, and for larger volumes, power absorptions are closer. It is not, we cannot make as definite a statement. But overall, we can still say that the simultaneous heating kind of follows, or pretty much follows, how the two materials would behave individually. Our final subsection is about having metal foils next to food as in packaging, and how does that change the electromagnetic field, this one here. So now this is referred to as active packaging as opposed to passive materials that do not heat in microwave, like paper, that does not change the electromagnetic pattern any significantly. So we want to talk about this presence of metal here in active packaging, but I would like you to see that there are entire books written on active packaging. So this is a complex area, lots of technologies are there, and lots of so we just want to get a feel for maybe two of the possibilities. Okay, so this is a vast area and the person watching the video is referred to books that are already available. As I said, I'll talk about two possibilities, and one is the use of foil, metal foil, for field modification, like you see here. So in this package, here is going to be metal foils placed for local field modification, and the other one is use of thin metallized film. So this thing has thin metallized film, thin metallized film called susceptors that do surface heating. So we're going to look at them in detail. One active packaging concept is to use a material such as a metal foil, such as aluminum foil, that reacts very differently to microwave to locally change the microwave pattern. Since corners and edges heat more, as we discussed earlier, and that's undesirable, so it makes sense people have tried to reduce that using this metal foil concept. And so here is a patented package having metal foil around the edges and corners. So you see metal foil here, metal foil around the edge and the corner. You can see metal foil here, and with no metal foil on the floor, on the transparent. So it's just trying to protect or prevent the edges and corners to overheat. So this is from a US patent, as you see the patent number. So how does it work? So there is normally edge overheating, and so we put the foil around and around the edge, and what that does is it shields the edges and the corners, and so this reduces the overheating of the edges, and that's how it makes the heating more uniform. Another important example of active packaging is the use of susceptors. So here we see a pie, a frozen pie, sitting on a paper bowl, but the paper bowl is not this one. That is just paper. It has a layer of a thin metallized film on the paper surface. That is what is referred to as the susceptor, and what it does is it absorbs microwaves readily, and it heats up to really high temperatures, and this can be seen in these thermal infrared camera pictures where both the bowl with the metal film and without the metal film, without any food present there, either case there's no food, and that's heated for 5 seconds, and then the infrared camera takes the picture, and you can clearly see that the one with susceptor is a lot hotter than, of course, paper, which does not even absorb microwave energy. By the way, the fact that you see a pattern, it's only on one side and not throughout, that has more to do with the oven patterns and the fact that turntable was not used. So you pick up the oven highs and lows, but still, if you place it the same way, you can compare with metal film and without, and you can see vast difference in temperature. So when it gets this hot, then it can emulate conventional surface heating. So it will be heating from the surface. It can remove moisture from the surface, keep food crispy, and all the advantages of conventional heating. So that emulation of the conventional heating is the primary application of susceptors. But in the big picture, you see this is another example of active packaging where the electric field or the heating pattern is manipulated using material that is microwave active and having them right next to the food.